Okay, I think the recording has started. So, welcome to the Bangalore Theory Seminar. It is my pleasure to introduce Jack. So, Jack is a PhD student at the University of Copenhagen, advised by Mikkel Abrahamsen. He previously received his Master of Mathematics from the University of Cambridge. His research interests include computational geometry and the existential theory of the reals. So, today he is going to talk about packing unit squares in simple polygons. Over to Jack.
Thanks for the introduction. Sorry, I'm just trying to get this slideshow to stop autoplaying. I said, okay. I think it has stopped autoplaying now. Okay. Yep. Thanks for the introduction. As you said, my name is Jack. I'm going to talk about this paper written with my advisor, Mikkel Abrahamsen, which is called, well, the name of the presentation is Packing Axis-Aligned Unit Squares into Simple Polygons is NP-hard. And this work is going to appear at Fox this fall. And now I can't. Sorry about that. This is very. There we go. Okay. So what's the problem that we're interested in? So I have K. I have a polygon P. I have K identical squares, and I want to know if I can pack them into the polygon without rotating. So just a very simple packing problem, a bunch of identical squares, polygonal domain. And as far back as 1981, this has been known to be NP-hard, but only in this sort of situation that you see here where the polygon can have holes in it. So not necessarily a simple polygon. So it's been an open question, at least since then, whether this is also hard for simple polygons or whether there's an algorithm for it. And our new result is that this is NP-hard, even when you're working with a simple polygon. So, and in fact, we can have these additional conditions that this is hard, even if the polygon is an orthogonal polygon with integer coordinates, and all the squares have size 2 by 2. And actually, with those conditions, we sort of disprove this conjecture from 2001 by Baur and Fekete, who conjectured that there should be a polynomial time algorithm to solve at least this restricted form of the packing. But our new result shows that that's not true unless P is equal to NP. So
one question, Jack, is some algorithmic results known for this problem, like approximation algorithms?
Oh yeah, that's a great question. So there's a p-task for this problem, so there's pretty good approximation algorithms known. So this is just this is just for the sort of exact version. Yes, there are good approximation algorithms known for this. And please feel free to chime in with questions at any time. But I guess the sort of question that I want to sort of start with is why you might believe that there might be an algorithm for simple polygons when it's NP-hard for polygons with holes. And the reason is that given a polygon with holes, you can sort of construct a polygon shaped like this sort of complicated graph. And this graph sort of represents like a instance of planar 3-sat. But if you try to do something like that with a polygon that doesn't have holes, a polygon that doesn't have holes sort of always looks a little bit like a tree. And in particular, on trees, you can often do sort of dynamic programming. So we could think about what that might look like. What we need to be able to do in order to have a dynamic programming solution is we would need to be able to sort of cut this polygon into 2 pieces. And then we need to be able to claim that the sort of complexity of whatever happens on that boundary is only sort of polynomial in size. And in principle, that isn't true. So in principle, if I sort of cut a polygon, I mean, if I have sort of n squares across, then, it's exponential in n how many different ways that boundary can look like. But the sort of question that we really need to answer is, do optimal packings actually look like that? And the answer is yes, that optimal packings actually can have sort of a quite complicated sequence of squares floating out in the middle of space, sort of arbitrarily far from the boundary. But this is something I'd like to present as sort of an overarching theme for this talk, which is how can we cause something complex to occur far from the polygon boundary? Because that's what we really need to do if we're going to defeat these sort of dynamic programming strategies. So now I'm going to get into how this reduction works. The first thing we need to do an NP hardness proof is to choose a problem to reduce from. And this is a little bit difficult because there aren't that many problems that look like simple polygons. And some of the text is getting cut off. Sorry about that. Actually, the problem we're going to use is a version of planar 3-sat, but we're going to use it in kind of a planar way. So this problem, monotone planar 3-sat, we have a 3-sat instance, and we also have this graph where we have an edge between a vertex and a clause whenever, or between a variable and a clause whenever that variable appears in that clause. And we have and so the instance is going to include a planar embedding of that graph, and we want to even be able to put a cycle through all the variable vertices in that planar embedding too. So you can see in this drawing over here, we have this planar graph, and then we also have a cycle through these variable vertices. And then we can enforce this additional condition. This cycle cuts the sort of clause vertices into two sets. And we want to say that the clause vertices outside this cycle are all positive. So you can see in this formula up here, all these variables, they appear non-negated in these clauses, and then the clauses that are inside the cycle, they appear negated. And that's where this monotone comes from. And actually, even this restricted version of 3-sat, this is still known to be NP hard. There's a detailed proof of this in this paper from 2012. Excuse me. Now, what we're going to do is I have this diagram over here on the right, and actually I'm going to convert this planar graph drawing into a diagram on the right. So every vertex is going to become a horizontal segment, and every edge is going to become a vertical segment, and the sort of top and bottom of that edge tell you what vertical segment, tell you what vertices that edge goes between. Can everyone see my cursor?
Yes, we can see.
Okay, thanks. So what we can sort of see here is that actually all of these variables in this planar graph, they become these horizontal. Okay, don't. Sorry about that. All the variables in this graph become these horizontal rows, and then the columns become these vertical things. And in order to be able to draw this graph like this, we actually use planarity. So the planarity of this graph, the fact that this graph is planar, sort of exactly tells us that I can draw it in this form. So we can see, for example, that like this clause C2 up here, this needs to connect to the variables x1, x2, and x3. But then this clause C1 sort of blocks it from connecting to variables beyond that, and that's sort of just exactly the condition that sort of this edge here doesn't cross this edge. So we get this sort of structure, and this now sort of looks like a simple polygon because actually all of these sort of important points where we have the ends of the column, those all end up on the sort of outer face of a simple polygon. And we have, is that a question?
Hi, yeah. So I had a question. So essentially, in this monotone planar 3-sat version, you have these C1, for example, on top of C2 and C3, right? So from what I understand, you do it in reverse when constructing. Yeah. Right. Okay.
So the outermost clause here becomes sort of the one that's closest to the variables, and then they go in reverse order.
Okay. Perfect. Thanks.
Any other questions? Okay. Anyways, the next thing we want to do is, right now we have some sort of rows that are clauses and some rows that are variables. And we have these crossings. And a sort of technical condition that we'll need later is that we don't want to have a crossing between one of these columns and a clause row. So what we're going to do is we're going to, okay, so what we're going to do is we're going to add some auxiliary variables. So each clause row is now getting sort of 3 variable rows. And then those 3 variable rows are connecting up to a clause. And you can see these short little red clause segments. Each of these now doesn't actually cross any of the columns. It only contacts the endpoints of the columns, and those are the columns that sort of the clause is supposed to be operating on. And we can also see all of these orange columns. These each represent, when they go between 2 variable rows, between 2 green rows, they always represent a constraint like top variable implies bottom variable. And all these clause rows, it always looks like the clauses are always sort of, the condition we want to have is that when we have a sort of orange column that goes down from a variable row, we want that condition to be easier to satisfy when the variable is negative, and when it goes up from the variable row, that condition is supposed to be easier to satisfy when the variable is positive. So we get this sort of monotonicity condition, which is going to be sort of very helpful for putting things together. And that's why we need this monotone planar 3 set. It just makes everything much simpler. The strategy, now we have this sort of polygon-shaped schematic, and we're just going to sort of we're going to draw a polygon that's sort of shaped like this schematic. And in order to do this NP hardness reduction, we sort of have 2 directions. We want to be able to say that if there is a satisfying assignment, then we can always pack this polygon in a particular way. That's not that hard. We can just sort of draw how to pack all of our gadgets. But then we need the other direction, and we need to say that any packing with some number of squares needs to satisfy certain conditions, and that's harder. So that's where we're going to need to do something clever. And the sort of idea for this is continuity. So if I give you this sort of square here, I hope everyone believes me when I say that there's a unique way to pack exactly 16 squares into this square. I could prove that in several ways, but I think it's more or less obvious. But actually, if I make the square sort of epsilon bigger, well, now there isn't a unique way to pack 16 squares, but you would sort of expect that for small enough epsilon, it's not going to change what the packings look like too much. And this is sort of a continuity property. We would expect any sort of sufficiently well-posed geometric problem to have some sort of property like this. We'd like to be able to say that if we make things to epsilon bigger, then the sort of structures of the solution shouldn't change too much. And okay, so now, I mean, that's a nice idea, but we need to prove it a little bit more rigorously. So in order to do that, yes? Question?
So what is epsilon? It's a constant, or it's some like 1 by n, any value it can be?
So it turns out in this case where with epsilon, in the case where you don't allow rotations, then epsilon can be then epsilon can be pretty large. So in this case, it can be up to like depending on how you can define it, can be like up to half the size of a square before you start introducing weird things. If you do this with other geometric problems, then the size of epsilon might depend on the size of your polygon. But in this sort of simple setting, it doesn't. It doesn't actually depend on how many squares there are. Does that answer your question?
Yes.
Okay. In order to sort of get a rigorous form of this result, the first thing I want to do is I want to restrict to looking at integer packings, which is a little weird because, I mean, continuity results over the integers seems weird, but this just makes everything easier. Because we're in this setting where the polygon has integer coordinates and all the squares have integer sizes, we can always just sort of shift the packing over until everything has an integer coordinate. There's a rigorous proof in this 2001 paper, if you're not convinced, but this is helpful. The next thing we're going to do, we're going to define a sort of regular grid that I'm going to call reference centers. These are just 1 by 1 unit squares in a regular grid throughout the entire plane. And the interesting thing about this now is that anywhere I put a square, in this grid, it covers exactly one reference center. So as long as this square has integer coordinates, there's exactly one reference center that is inside this square and can't be contained in any other squares in a packing. Was there a question?
Hi, yeah. So in the previous paper by Chandar, could you go through could you show that again on the previous page?
This one?
So so all the vertices of all squares are integers. Is that what it says?
Yeah, so I can, so precisely what it says is that if I can find a packing of some size, then I can always find a packing of the same size where all the vertices are integers.
I see. Okay, cool, thanks.
Yep. Okay, so now what I'm going to do is I'm going to take some polygon. I'm going to put these this grid of reference centers on top of it. There are sort of 4 distinct ways to do that, and later we'll sort of choose the way, the one way that gives us the most useful result. And in this case, if you count them, there should be 14 reference centers. And any way I pack a square into the polygon, that square has to contain exactly one reference center. So any way of packing 14 squares into this polygon, I know that every square contains exactly one reference center. So this is kind of neat because you can see there's like a gap in this packing here. And in general, this sort of, I'm going to call it a full packing when there's one square per reference center. And in general, in a full packing, there can be lots of gaps. But sort of amazingly, if we know it's a full packing, we know these gaps can never occur on reference centers. So that's quite useful. And I'm claiming this is a sort of form of continuity result. And just to relate that back, if I put a square around each reference center right in the center, then I get this sort of polygon that now this is a sort of polygon that can be tightly packed that approximates this original polygon. And so now my result's claiming that the sort of packings of this bigger polygon approximate this approximation, this tightly packable polygon. And the reason I'm sort of stressing this continuity is because, excuse me, this result with the reference centers sort of looks like it's very specific to this problem, but it's not. This is really something you can do if you think about it as continuity. Oh, excuse me. If you think about this as continuity, you can really do this for lots of sort of related problems. You can come up with, you should be able to come up with some sort of related result. But back to our setting, back to the 2x2 square packing. What these reference centers allow us to do is, if I have a square here, and I know that I'm looking at a full packing, well, this square, the only way I can pack it into the polygon, it needs to sort of, it's only one way to have a square covering this reference center, but then actually the next reference center, there's only one way to pack a square covering that. And we can sort of push, there are two ways to pack this next square. Then all the way down, this square at the end, now we know there's only one square way to pack this. And this can be a sort of long section crossing the middle of the polygon. And we only have one way of packing this square at the end. So we've learned a lot. Assuming that we have this full packing, this tells us that something that happens way over on this side of the polygon can influence stuff that happens all the way over here without needing to know that much about the rest of the packing. Sorry. Okay, now I'm going to get into the actual gadgets, finally. Now we can start looking at these sorts of things. Now, first is our variable gadget. So each of these green rows in this schematic is a variable gadget or is a variable row. And these we need to create these corridors at the end of the row. So I've taken our schematic and drawn this black line around it because I'm creating a polygon shaped like the schematic. And now at these ends, I'm going to put these little variable gadget tunnels. So what I have is I have this little tunnel at the end, and if you look at these two squares with these blue reference centers, this gadget at the end is sort of set up so that one of them always pushes to the left, and one of them always pushes so that sort of, I guess what I should say is that if I look at these squares that are on the left, at least one of them has to push to the right. I can't have both of these sort of pushing in. There's not enough space. Same thing happens over here. And so what we know is out of these two rows that form this variable gadget, one has to push to the left and one has to push to the right. So we have these sort of two possible orientations. I'm going to call this one plus because the squares sort of go around in a counterclockwise direction, and this one's minus since the squares go around in a clockwise direction. And sort of plus is going to encode a variable that has a value of 1, and minus is going to encode a variable that has a value of -1.
So are they just mirror reflections? Just reflection or?
Which is reflection?
So, I mean, plus and minus, are they reflection of each other? If I place a mirror in between, is it just a reflection or?
Yes. Yes, yeah, that's true. That's one way of thinking about it. I think about it, I prefer to think about it as sort of clockwise versus counterclockwise, but that's, yeah, it is, they are a mirror reflection, but not everything in the construction sort of has mirror symmetry. There's a bunch of like weird parity choices, so you have to be a little careful, but that'll actually come up in this next section. Now we're going to start creating constraints between variables. So that's sort of wherever the endpoint of these columns are. So we have these two push gadgets. So we have at the top here, we have a what I call a push down if plus gadget. So if the variable gadget's in the plus condition, then it forces this square here to push down. So what I have here is below the two rows for the variable gadget, I have a static row. So this is a row that doesn't move at all horizontally. The horizontal positions of this are always fixed. And so I can see that this gadget over here, I let these two red squares raise up, but depending on the position of the gadget, I may or may not allow this square with the orange reference center to push up. And then I have a sort of similar thing on the bottom where I have a little indent pushing up, and that pushes some squares up. And if the variable gadget on the bottom is minus, then is in the minus position, then I push up on this orange square, but otherwise it's allowed to push down. And so you can see if I sort of were to combine these together, it would create a constraint like top variable implies bottom variable. And this is why is it doing that? This is where this sort of parity thing comes in, because these static rows, all the squares push to the left relative to their reference centers. So they always have the reference centers in these sort of top right quadrant, or in the sort of right side. And this actually kind of creates a constraint. If you mess around with it, what you'll realize is that if you wanted to have a push down if minus gadget or a push up if plus gadget, then you would actually need to have the static rows pushing the other direction. And because they're static, they can't push both directions, and so we actually have to sort of choose one of them. And that's where we're using this monotone planar 3 set, so that we sort of have the bottom is always easier to satisfy. Just the sort of, if it's on the bottom of a column, it's always easier to satisfy if it's plus, and if it's on the top, it's always easier to satisfy if it's minus. Now, I guess you can sort of see from those diagrams how I would create this sort of constraint, this sort of A implies B constraint if two variables were right next to each other. And now we need to worry about these crossing. So now we're finally getting into stuff that's happening without actually using any edges of the polygon. And the interesting thing is that if we ever have a variable gadget and we have two static rows on either side of it, well, if I push up on these two squares in this static row, then that always forces these four squares up here to push up as well. And you can see that that's actually true regardless of which position this variable gadget is in. So we can sort of get these sort of signals to pass through each other without actually interfering with each other at all. And now you can see also if I push up on this sort of orange square, that pushes the corresponding orange square on the other side up. So we have a sort of schematic of how we create this constraint. We have a variable on the top and a variable at the bottom. This variable at the top is connected to a push up if, I think it was push up if plus, and then the bottom is, oh, hang on. Push down if plus, and push up if minus on the bottom. And we have this sort of inverted pyramid shape. So we have this sort of big section in the inverted pyramid that always pushes up. The stuff around it always pushes down. And then we have one column on the side that sort of can push up or down. And if both variables push on that column, then that's bad and we won't be able to pack. But otherwise, we'll be able to satisfy this. You'll notice that the pyramid, it might need to get pretty wide.
Sorry, Jack.
So,
Jack, can you go to the previous slide once more?
This one?
So what is the difference between these two? Like, I mean, both are feasible. Like in one case, you are just orange things are pushed down, and remaining things are same.
So in both of these cases are feasible, but there might be a case where the top thing is trying to push. Where the top thing is trying to push down and the bottom thing is trying to push up. So if we look at this top left thing and this bottom right thing, those would be pushing against each other.
I see. Yeah, fine.
Okay, good question. But now, because these pyramids are getting wider as they go up, these push gadgets, these push down gadgets, actually I need to make them potentially arbitrarily wide. That's fine. We can just sort of literally just make them wider, but if you're doing the whole reduction in detail, you'd have to, do a little bit of bookkeeping to keep track of this sort of thing. But well, because it's a pyramid, the top is getting wider, so that's this. But now finally, 2sat is solvable in polynomial time, so we need to have some sort of constraint that depends on 3 variables. And finally, we're going to draw some OR gadgets. Here's the positive OR gadget. So we have these we have just the tops of sort of these pyramids that are created by push up gadgets. And in this situation, where all of these squares, all of these push squares push up, we can't actually pack this. This square up here sort of would have to stick out. But if this square here could push down, then we'd make space. If this square here is allowed to push down, then it allows some of these squares on top to shift over. Same here. I have drawings of that here. So you can see if I allow any of these three sort of push squares to push down, then I can pack this thing. I also need to worry a little bit. This is why some of the reference center things are really helpful, because I also need to worry about the case where what if everything pushes down, and then we actually introduce a lot of slack. And this is sort of why we can't have a column crossing through this OR gadget. This is why we need to sort of isolate them, because we have these slack cases, and it's very hard to prevent that slack from sort of propagating out. So we need to keep these OR gadgets sort of off in their own little corner. Now, here's just a nice diagram with a whole bunch of squares. We have three variable gadgets, and they're all connected up to an OR gadget up here. Just a neat diagram. And now, actually, okay, last thing we need to do, there's also a negative OR gadget. And again, this is something you might think it should be a mirror image, but because of some of these choices of parity, the fact that our pyramids are inverted pyramids, it's not exactly a mirror image, but it's pretty much the same thing. Instead, now we have sort of the bases of these pyramids here, and now we have these push squares and these push up. You might notice that the push squares are on the right side of the pyramids. That's another weird parity thing. I won't go into too much detail on that. But now we sort of have everything, right? We can make everything in the schematic. We can make the variable gadgets. We can make these push gadgets that create constraints between two variables. We can make the OR gadgets that create constraint between three variables. And we can put everything together. And I'm going to claim that now we've done an NP hardness reduction. So just to check, we're given this instance of this NP hard problem monotone planar 3-sat. I'm going to give you an polygon. Might have to do a little bit of bookkeeping, but I give you this polygon. Everything is polynomial in size. And I give you this polygon that contains k reference centers. I've shown you how to pack everything. If there's a satisfying assignment, I just choose the orientation.
What was K? Was it the number of claws? I forgot.
That's the number of squares.
Okay.
So if you remember, when I defined this problem, I think I said
from SAT, how are you getting these squares? Given a formula phi, if there are m clauses and n variables, how many squares do you get then?
It's probably quite complicated in order to come up with the exact number. I think in the paper we figured out asymptotically roughly how many it is. It's probably, I think it was n to the 4th or n to the 5th, something like that.
Okay.
Depending on whether you reduce, I guess you already have a polynomial blow up going from 3-sat to planar 3-sat. So there's some, depending on how you count what you get originally. But
thanks.
Yep. And it's important, it's important that it's exactly k squares again, but the point is that if I give you a satisfying assignment, I can set the orientation of each variable gadgets according to those variables, and then I should be able to pack all the push gadgets and all the OR gadgets because it satisfies the formula. And then we actually have the converse, because any packing with squares gives us, we can read off the values of the variables by looking at the orientation that the variable gadgets get packed. And this tells us, because of the push gadgets and OR gadgets, we know that this means that those variable assignments have to be compatible with the constraints in phi. And this tells us that the problem's NP hard. And rather remarkably, In our paper, we even do this for orthogonally convex polygons. I do not have nearly enough time to even start explaining how that works. It's extremely complicated, but an orthogonally convex polygon is a polygon where the intersection of the polygon with every vertical or horizontal line is a single line segment. So it's a weaker version of convexity. And this was a sort of, this was a conjecture, this was another conjecture in some previous work on packing. Someone said that, well, if we can't find a polynomial time algorithm for simple polygons, maybe we should at least be able to do it for orthogonally convex polygons. But again, our results show that that's not true. You can't come up with an efficient algorithm even in that case unless P is equal to NP. I think I have time, so I'm going to talk a little bit. There's some other stuff we can do without too much work. Sort of dual to packing is covering. And so in covering, we just want to, we have a bunch of squares. Question?
Yeah, so this orthogonally convex polygon, it's not really a convex polygon, right? Like,
no, it's not convex. It's orthogonally convex.
Okay. Can you repeat the definition once more?
Yeah, so an orthogonally convex polygon is a polygon where the intersection with every vertical or horizontal line is a single segment. So convex means that the intersection with any line is a single segment, but now we're just restricting to horizontal and vertical lines.
Okay.
So if
Okay.
we look back, actually, I think, just as an example, I think if we look at just the outer part of this polygon, this is orthogonally convex if you ignore this hole.
Yeah. Thanks.
Yep. But, okay, so covering and so we have NP hardness of covering and partitioning. So if we want to cover, so we want to cover a polygon with a bunch of sort of unit squares. That's a very natural problem. This is another thing that had been known to be hard for polygons with holes, but wasn't known until now for simple polygons. And then there's a related problem where we want to partition a polygon into a bunch of pieces, and each piece has to fit inside a unit square. And the difference between those two problems is that in the partitioning problem, I guess, yeah, in the partitioning problem, we want each piece to be, so we want to partition it into pieces that are connected. So we would say that this thing can't be partitioned into two pieces because this piece up here is actually, that's not connected. But it turns out that under sort of certain reasonable assumptions on everything, it turns out that these problems are equivalent. So from now on, I'm just going to be looking at the covering case, and then the way you get to the partitioning case is actually just by taking a sort of Voronoi diagram. Yeah? Question?
Hi, so just to confirm, so you're saying that you want to cover an orthogonal polygon, I assume, with pieces that are small, right? That's essentially the question?
Yeah, so you want to cover it with pieces. Yeah, so I guess this is one definition. Describe P. Well, okay. Yeah, so you want to cover it with pieces that fit inside an axis-aligned unit square. Yeah.
Right. Okay. Cool. Thanks.
And there are a bunch of like slight variants depending on how exactly you want to deal with this like disconnected covering case. It turns out if you want to do this disconnected covering case, you can actually just sort of use the previous, you can actually just sort of use some of these reductions for polygons with holes, and you basically just connect the hole to the outside of the polygon using a really thin tunnel, and then sort of and then if you're allowed to have disconnected coverings, it sort of ends up being equivalent. So the sort of difference between polygons with and without holes becomes less interesting in that case. But in the cases we're restricting to, where everything's going to be an integer cover and all the squares are 2 by 2, then it becomes more equivalent. Yeah, was that a question?
Oh, sorry. So just to rephrase what you said, so what you're using inside the square to cover should be simply connected. That's essentially what you're saying, right?
Yes.
Okay, cool. Thanks.
Yeah. And then again, it turns out that as long as everything's an axis-aligned unit square, if you have a covering that satisfies this property that it's simply connected, then you can sort of take a Voronoi diagram, actually, using like a Chebyshev distance, using like a subnorm distance. And that will convert a covering into a partition where you have everything contained in sort of exactly one piece. So in this case, these problems are nearly equivalent. But if you allow rotations, you can have some weird stuff happening. Basically, the reduction is sort of, yeah, was that another question?
Yeah, sorry. So just to confirm, so you're saying that if you want to cover with small objects and it's an orthogonal polygon, then it's the number of objects you need is the same if you want to partition as well?
Under some, so not in general. You need a couple of conditions. So if small means fitting into an axis-aligned unit square, or I guess an axis-aligned 2 by 2 square, and the polygon has integer coordinates, and is an orthogonal polygon, I believe they're the same. If the square is larger than 2 by 2, I don't remember exactly. There might be some weird things that can happen.
Right. Okay.
But so, I think the idea is that typically, as long as you're using like symmetric, if you're covering with symmetric convex objects, then you can typically just do this sort of Voronoi diagram trick.
Okay, cool. That sounds very interesting. Thanks.
Yeah, I believe there's a proof of this. The paper's on arXiv. I can give you a link if anyone's interested. I think there's a proof of this that gives you the exact conditions under whether these things are equivalent. We have these reference centers. We're going to do something similar with reference centers, and I think possibly in the version we used, the fact that these reference centers exist helps to guarantee that you can always do this. But again, there's a proof in that paper, and I don't remember off the top of my head what the precise conditions you need for it to work are.
Yeah, I'd be very interested. Thanks.
Yeah. Okay, so anyways, we have these variable gadgets. So similar to the covering case, we have reference centers, and the same argument that, first of all, the same thing is true that you can always do an integer covering in this version of it. It's sort of the same type of argument where you just shift everything over. Now the result we get about the reference centers is that each reference center is contained in exactly one square. So some parts of the polygon might have an overlap, but there's never an overlap on top of a reference center if the number of squares is the same as the number of reference centers, because each square can only cover one reference center. Now we have these variable gadgets, and it's sort of very much the same sort of device where we have two things at the end, and now instead of pushing on rows, we pull on rows. So now if we look at these gadgets, one end has to pull on the top. We're either pulling on the top row or pulling on the bottom row, and so we create either a plus or minus position again. We have these pull gadgets instead of push gadgets now, so we have pull down if plus and pull up if minus. Again, there's some weird, there's a bunch of weird choices of parity, but it's a similar sort of thing where we can't have two gadgets pulling on the same thing. And now actually, instead of being an inverted pyramid, it's a right side up pyramid. Just happens to be how we did the construction. Any way you choose the parity, there's going to be a little bit of difference between the covering and the packing, but pretty much the same idea. Or gadget looks a little bit funky, but it's the same sort of thing where if any of these orange columns are allowed to push up, then it lets this top thing slide over. I have some drawings of that here. And if we let any of these columns push up, then we can cover everything. And then it's basically just the same sort of reduction. The negative OR gadget, I haven't drawn it, but it's pretty much a similar type of thing. And we get that this problem is hard for that this covering problem is hard as well. And then we can use some of our results to say that the partitioning is pretty much equivalent, at least for the specific instances we care about, the specific instances that appear in this reduction. So we also have now shown that partitioning is NP hard for simple polygons. So some other nice results using pretty much the same ideas. I'd like to briefly mention a couple of fun open problems. These are all problems that are known to be hard for polygons, and at least NP hard for polygons with holes, but where pretty much nothing is known about simple polygons. So one is packing squares with rotations. So, I mean, there's been quite a lot of work even just to finding the best way to pack, what's the smallest square you can pack 17 squares into. People have come up with some fun arrangements. But there's a sort of unrelated well, not unrelated, but there's a different problem that's maybe, I think this problem is very approachable. I think we should be able to do an NP hardness result for this problem too. I think it should be doable. I don't know exactly how. I would say the same about circle packing. So packing circles into a polygon. This is a little harder because you're never going to have a tight packing, so you're always going to have a little bit of space. But I would sort of expect that you can do something, that you could maybe work on that. Yeah, yes?
So, I mean, your results use the polygons to be like orthogonally convex. So there are bends on the boundary which you used, but the square packing with rotations or circle packing, you're showing a square container. Do you think it's still hard, or you need the
No, only if I'm using a sufficiently complicated polygon, not in square containers. Thanks for the clarification. Yeah, maybe I shouldn't have shown square containers. I mean, I don't think that seems, yeah. So I'm saying you can specify some complicated polygon, but still a simple polygon in the sense of not having holes. And I think these two problems should probably be NP hard, but again, I don't have a proof of that. And I think these are interesting open problems. But again, yeah, maybe I shouldn't have drawn squares here. Maybe I should have drawn slightly more complicated polygons. But
in general, even the previous result, does it extend to constant number of sides for a polygon? Like, I think that you need like some linear number of sides, or is it still possible to prove the hardness result even for some polygon with constant number of sides?
I think it would be really hard to do any sort of hardness result for a constant number of sides.
I see.
I'm really not. I mean, the reduction that I'm doing, the orthogonally convex one, you still need tons of sides. You definitely can't do it in any sort of constant number of sides. I think for orthogonal polygons with constant number of sides, for any constant number of sides, I think there's actually a result that for orthogonal polygons with integer coordinates and packing axis line 2 by 2 unit squares, I think that can't be NP hard. Like I think you can do that in polynomial time. I think the size of the packing can't be. I think the packing sort of can't be that much more complicated than I think the sort of the packing can be described as a bunch of like repeating sections, and that any there's always there's a paper. Let's see. I think it's. I can try to
Sure.
post a link to this paper, and they show that if you have these grid polygons, that actually the sort of size that this packing, the complexity of it, you can describe it in size that depends only on the number of vertices. So,
I see. So another question I have is instead of 2 cross 2 square, if I tell you like a tromino, like which is a 3 unit squares union, so is something known in that setting, whether it's polynomial solvable or it's hard as well?
So domino packing is pretty well understood, and I think that's known to be so packing with just a 1 by 2 dominoes where you're allowed 90-degree rotations. I think Mikkel actually has a paper on that, and I think even with holes, that's hard. This 1 by 3 case was something we were looking at, and we couldn't figure that out. I think that one is hard for polygons with holes, but that's another good example of a question.
No, so tromino can be also L-shaped basically.
Right. Yeah, that makes it. Yeah. So the maximum number of trominos, yeah, that's even harder. I don't think. Assuming if you took only one tromino, if you took like one L shape, and you don't allow any rotations or any other packings, and you want to pack a bunch of identical shapes, that you might be able to approach with this sort of technique. I'm not certain about that, but that seems like it might be that seems like the type of thing you might be able to do. But otherwise, I don't think so. Except what you can do if you're packing trominos in a polygon that's if you're packing trominos, if you drop the condition that the coordinates have to be integers, then I think you can do it. So if you allow the coordinates to be more complicated, then I think you can do, almost any shape that's made of squares, because I think you can do a version of this reduction where you use the same sort of argument to reason about squares, the individual squares, but then when an optimal packing exists, you can also do it using these sort of tromino shapes. I think something like that's possible. I don't know if that makes a ton of sense.
Thanks.
But yeah, so other great examples of open problems, I think when it comes to, hardness results for these sort of simple polygons, I think very little is known in terms of sort of packing and partitioning problems for simple polygons. Especially when you're dealing with like identical pieces. But a couple other problems I just wanted to point out quickly that we think are interesting. Minimum non-obtuse triangulation. So you want to triangulate a polygon, and you're not allowed to use angles larger than 90 degrees. There are some papers it's actually fairly non-trivial even to show that you can always find these triangulations. So I believe it is known that it's NP hard for polygons with holes to find a minimum non-obtuse triangulation, but I don't think it's known for polygons without holes. Then another very practically motivated problem is shortest milling path. So I want to sort of make an object with a 3D printer or cut it out with a mill, and I want to know how long a path I need to cut it out. And obviously, this is a very important problem in manufacturing. And in terms of finding the exact optimum, it's hard for polygons with holes, but again, not very little is known about simple polygons. So I think I have some time to answer some questions. If anyone has any questions, yeah?
Hey, so when you're talking about the square packing with rotations, obviously if you say that all vertices must be integers, then I'm assuming you can't allow rotations at all, right? Then it will just be axis-aligned squares again. So is that right?
I'm not sure I understand what you're saying.
So if you force all vertices of the stuff that you're packing with to be integers, then you can't allow any rotation at all, right? Because if you rotate it a bit,
yeah. Yes, at least for 2 by 2.
Right.
Yeah, I suppose if you're doing like 5 by 5, then you can start putting rotated squares with vertices on an integer grid.
Yes.
But yeah, in general, you get complicated irrational numbers. And actually, I'm pretty sure the version, this square packing with rotations, I'm pretty sure this problem, if the polygons have holes, I think that's, I've sketched this. I don't think this is, you can find a proof of this anywhere, but it looks like that's probably even exists are hard.
I see. So what happens if you force at least one vertex per polygon to be on the grid? So essentially what I'm trying to say is that you can describe each square nicely somehow. So you can say, well, it's anchored to this grid point at this angle, something like that. So it's, yeah.
I mean, something like that. Yeah, I'm not sure how much that, probably if you did something like that, I would expect something like that would make it easier. Because it's actually very hard. It's actually very hard, this square packing with rotations, it's actually very hard to sort of, I think it's very hard to have a good intuition of what it looks like. So, I mean, you can come up with some of these polygons. You can come up with some of these, some of these sorts of gadgets. And there's a question of like, if I allow rotations, could I pack this with fewer squares? Like, it's not obvious whether you can. I think you probably can, but in general, but it's really unclear how you would do that. So it's quite, I think, yeah, I think that problem in general is pretty hard to reason about.
And just to confirm your result about like the number of packing stuff and the number of covering stuff being equal, that doesn't work anymore, right? If you allow rotations, is that true?
So the continuity result. So the way I proved it, it definitely doesn't work. However, I think I mentioned earlier that for some other problems, if you allow epsilon to depend on the number of squares, then I think it does work. So if you start with a polygon that can be tiled exactly, and make it bigger by sort of epsilon, where epsilon is going to be, I think when I was calculating this, it was something like 1 over n to the 6th, roughly, was the numbers I was getting. And you can show that if you make it only a tiny bit bigger, like that much bigger, then when you're looking at these things that can be packed with rotations, even if you allow rotations, you get some sort of result that the packing has to look sort of similar. That the square if you only that if you make the square bigger by epsilon, then the positions of all the squares inside can change by like epsilon plus n to the 6th epsilon squared or something. And something similar is true with circle packing. So you can typically make some version of this continuity result work, but it's much weaker.
Cool, thanks.
Okay, so Jack, so one question, like your result showed that showed this for like 2 cross 2 squares, but does it also imply that checking if a given number of 3 cross 3 squares is hard? Checking if a given number of 3 cross 3 squares can be packed is hard or not? Or let's say n cross n in general.
So it proves n times n for every even n. It does
Okay.
not immediately give you 3 by 3, but it's not that hard to extend it to any number.
I see. Okay.
But it's not you can't get that immediately. You need to make new gadgets for sort of. I think you need to make special gadgets for sort of 3 by 3 and maybe 4 by 4, and then once you get to 5 by 5 and bigger, you can just sort of you can sort of say that you're doing the same thing for everything. But for the smaller numbers, there's a little bit of weird stuff that goes on, and it might not be exactly the same. But yeah, you can do it for any size of square.
All right. Thanks.
So another question I have, if I mean, you showed NP hardness for unit squares. By considering more complicated objects, is it possible to show APX hardness for some other complicated shapes of objects using your constructions?
So APX hardness?
Yeah. So whether, I mean, given, yeah, even getting a pitas is hard for some particular types of objects. Like, for example, simple question like 2D knapsack with rectangles and unit square, it's not clear the question is APX hard or not, for example. So those are open questions. But in your case, we have a polygon which is orthogonally convex, and also we give arbitrary objects. Maybe they're not unit squares, but let's say any rectangle, any rectangle. Is it possible to show APX hardness or these gadgets? Do you see any other applications in other problems, related problems?
I'm not really sure. It seems like it would be difficult to use these techniques for APX hardness because typically with these sort of continuity results, as soon as you remove even just like one square, everything starts to fall apart. So I mean, APX hardness results typically make use of a lot of these results are making use of some sort of like probabilistically checkable proof. You know, a lot of the time in order to get these results, you need some more sophisticated results than sort of just directly doing a reduction.
You know, a lot of these are just black box kind of thing also from some other problems. Like you don't need PCP always. If you know some problem is already APX hard, you can do approximation preserving reduction or L reduction and show hardness for problems as well. So some problems, for example, if you have rectangles and you pack them minimum number of square bins, that's APX hard, for example. That uses some other kind of reduction from 3-dimensional matching. But also what you can do is, I mean, you can break this problem into multiple smaller problems, and within the smaller problems, even losing one square is a problem. but maybe you can repeat the gadget many times and then you can still lose a constant fraction of the squares. But anyway, I mean, it's a, yeah, maybe we can talk offline about it.
Yeah, I mean, it's a great question. I haven't thought a ton about that, but you would definitely need some new techniques, but it's not impossible that something like that could work. But actually, well, for this specific example, I sort of expect, for the specific example of, well, I guess in this example, we already know there's a p-task, so you need to come up with a problem that where a p-task isn't known.
Yeah, that's why I'm saying the object should not be unit squares, about 2 cross 2 squares. It should be some more complicated object like rectangles or something else.
Yeah.
Yeah. Anyway, thanks.
Yep. Okay. Any more questions?
Yeah, I think no. Let me stop the recording.